So in the last couple of lectures, we talked about a method called Kruskal's algorithm for finding the minimum spanning tree of a weighted graph. In this lecture, we're going to look at another approach, something called Prim's algorithm, that really comes at the question from a very different direction. Kruskal's algorithm is very top-down. It starts with the entire graph, finds the best possible edge, and adds it. And it keeps working its way down, picking pieces out of the graph as a whole until it gets to the answer. Prim's algorithm goes the other way. Prim's algorithm, and I've got the process here, starts by saying, okay, look, pick a vertex to start with. Doesn't matter which one. Pick any vertex. Add to our final result the lowest cost edge coming out of that vertex. Then repeat the process. Take a look at the two vertices that we now have. Find the lowest possible edge connecting to one of those two, adjacent to one of those two, and add it. And it keeps building and extending our graph out from a starting point, from an individual vertex. Okay, so you can read through the process here if you want to read the whole algorithm, but let's take a look at an example and see how this works. So I have a graph here for us to take a look at. This is actually the same graph that we used a couple lectures back when we were looking at an example of Kruskal's algorithm. But I'm going to redo this, right? We'll do this with Prim's algorithm and see what happens. So I'm going to decide to start somewhat arbitrarily from CHM. I'm thinking that's the chemistry building. Remember that this was supposed to be the a graph of the buildings in a small college campus. So because I've added that one to my output, I'm going to remove it from the original graph so I don't accidentally duplicate. Now, what I'm going to do is I'm going to look at all of the edges coming out of that vertex. There's only two of them. One is 88 and one is 91. I'm going to take the smallest one and add that to my output. It's going to be the 88 going to the CAT building. And then I'm going to remove the CAT option from the original graph. Now, we do the same thing. We look at all of the edges coming out of this graph. We're going to look at the 91 to ALB. We're going to look at the 112 to ALB. We're going to look at the 244 and the 150. The 91 to that ALB building is the smallest of the bunch, so that's the one that gets added. And again, I'm going to remove ALB from the original graph. Now, we've got, what do we have? 4 options now. We've got the 150 to BSC, the 244 to EEL, we've got the 112, and we've got the 125. Now that 112 objectively is the best one, right? Because it's the smallest of the lot. But I can't add it because if I add it, it's going to create a circuit. And we don't want to ever create a circuit in our output, otherwise it's not going to be a tree. So, of the remaining 3, the 125 to the TTY building is the lowest, so that's the one I'll add. We'll take TTY out of the mix. Now, again, disregarding the 112, I've got the 150 to BSC, the 244 to EEL, the 100 to EEL, and the 99 to the MAC building. 99 is the smallest of the bunch, so that's the one that gets added. And again, we're going to take MAC out. Now, you can kind of scan through here yourself. Hopefully, you're getting the hang of this by now. The next lowest is going to be the 88 to the EEL building. And now we're down to 2 options. The 244, the 100, and the 112, those are out because they all create circuits, which means we have to choose between the 180 and the 150. The 150 is the smaller. That's the one that gets added. And now we've made our way through all of the edges. We've made our way through all of the vertices, right? Every vertex from the original graph has been added to our output. So this is the result of Prim's algorithm. And if you remember from the previous lecture, this is actually the same result we got from Kruskal's algorithm as well. Okay, so but before we move on, I want to talk for just a minute to the computer science people in the room. Kruskal's algorithm and Prim's algorithm are both examples of what are called greedy algorithms. In computer science, a greedy algorithm is one that derives its solution by making a series of choices. In both of these algorithms, we were constantly choosing the next vertex, the next edge to add. And it never goes back and revisits a choice. So you may find yourself at a point in an algorithm, for example, where your next choice is to add something that is objectively bad, a really high weight edge, for example. A greedy algorithm would never go back and say, well, look, is there a point where I could have made a better choice? A choice that may not have been the lowest choice at that moment, but that led us to better choices later on. Right? Greedy algorithms never look backwards. A consequence of this is the greedy algorithms don't always give the absolute best solution. With some algorithms, the best you can hope for is an approximate solution, one that's reasonably good. As we saw, that's not the case with Kruskal's algorithm. Kruskal's algorithm, we proved its correctness. In other words, we showed that it does give the exact result every time. And looking ahead to the next lecture in the series here, we're going to do the same thing for Prim's algorithm. We're going to show that Prim's algorithm is also correct in the sense that we can count on it to always give us the correct result. Now, if you're not into the whole super theoretical showing correctness side, that's perfectly fine. You can jump ahead to the next lecture after this, where we're going to talk about another path-finding algorithm called Dijkstra's algorithm.